Scientists at the European Organization for Nuclear Research recently discovered that when they packed 40% more protons into a single beam, one specific part of the machine began to behave in a way that defied every computer model. Why did the world's most powerful particle accelerator suddenly start to overheat when it was supposed to be operating well within its safety limits? This is the central question of the current third run of the Large Hadron Collider, and by the end of this video, you will understand exactly how a tiny piece of metal deep inside the vacuum system is currently threatening the future of particle physics. We are going to look at the hidden mechanism of impedance heating and why the evidence shows that the old way of calculating beam stability is no longer enough to keep the machine safe. Before we finish, I will show you the exact verdict on why Beam 1 is failing where Beam 2 is succeeding, and what this means for the massive upgrade planned for the end of this decade. To understand this, we have to look at the simple reality of what happens when you try to move more matter through a pipe than it was ever designed to handle. Normally, scientists explain the Large Hadron Collider as a giant circle where particles crash into each other. But the visible clue that something is wrong is not found in the collisions themselves. Instead, it is found in the temperature sensors of the vacuum modules. When the intensity was pushed to 230 billion protons per bunch, the sensors did not just rise slightly. They spiked in a pattern that suggested the beam was physically dragging the hardware along with it. This was the first sign that the standard model of how a vacuum should behave was missing a critical variable. The old model of the Large Hadron Collider assumed that as long as the magnets were cold and the vacuum was empty, the beam could pass through without any friction. Because protons are subatomic particles, they are not supposed to experience wind resistance or physical rubbing against the walls of the pipe. However, the contradiction lies in the fact that even in a perfect vacuum, a beam of charged particles creates an electromagnetic wake. Think of it like a boat moving through water. Even if the boat does not touch the shore, the waves it creates will eventually hit the land. In the Large Hadron Collider, these electromagnetic waves are called wake fields. And when the proton intensity increased by 40%, these waves became powerful enough to start vibrating the metal components of the machine itself. This is why the engineers began to see heat in places where no particles were actually hitting the walls. This phenomenon is known as impedance heating, and it is the primary reason why the machine is currently struggling to settle. When you have 230 billion protons moving at nearly the speed of light, they generate an enormous amount of electrical resistance in the surrounding copper and steel. The scientific contradiction here is that the resistance is not coming from the particles themselves, but from the mirror charges they induce in the walls of the vacuum chamber. As the protons fly by, they pull electrons along the surface of the metal. If the metal is not perfectly smooth, or if there are gaps in the shielding, those moving electrons create heat through simple electrical resistance. This heat is what the operators are now fighting to control. One of the most delicate parts of this system is a component called the radio frequency fingers. These are tiny metallic strips designed to maintain electrical continuity between different sections of the beam pipe while allowing for thermal expansion. If the impedance heating becomes too intense, these fingers can actually warp or bend out of shape. If a single finger deforms and pokes into the path of the beam, it would be like a high-speed train hitting a steel bar. The evidence from the 2025 tests showed that Beam 1 is specifically vulnerable to this kind of deformation. This suggests that there is a physical misalignment or a manufacturing flaw in the vacuum modules of the first beamline that does not exist in the second. The engineers now face a difficult choice because the Large Hadron Collider is split into 8 independent sectors. Each sector is a massive engineering project on its own, protected by a 3-stage system designed to catch stray particles. This shielding is so effective that in the entire history of the machine, there have only been 17 times when the beam caused a magnet to lose its superconducting state, an event known as a quench. Remarkably, 8 of those 17 events were done on purpose by scientists who wanted to see how much the magnets could take. This proves that the magnets themselves are incredibly stable, but the new heating problem is not happening in the magnets. It is happening in the spaces between them. This shift in the failure point is what has the team at the European Organization for Nuclear Research so concerned. To test the limits of the machine without actually breaking it, the operators use a technique called transverse blow-up. They inject a specific type of electronic noise, known as white noise, into the feedback loop that controls the beam. This causes the beam to grow slightly larger in diameter, allowing it to brush against the safety sensors. This is a controlled way of measuring the aperture, or the physical opening of the pipe. During the high-intensity tests, this technique revealed that the safety margins are much thinner than previously thought. The evidence shows that the 40% increase in protons has narrowed the window of error to almost zero, meaning any small vibration could lead to a total loss of the beam. The scale of the energy involved here is difficult to wrap your head around. Currently, the Large Hadron Collider routinely stores over 450 megajoules of energy in the beam. To put that in perspective, that is roughly the same kinetic energy as a high-speed passenger train traveling at over 150 kilometers per hour. The goal for the future High Luminosity upgrade is to reach 700 megajoules. When the intensity was pushed to 40% above the standard, the machine was handling energy levels that it was never truly built to sustain for long periods. This is why the one-magnet sector would not settle. The sheer amount of energy was creating a feedback loop of heat that the cooling systems could not keep up with. During these dedicated tests, the engineers did not fill the entire ring. Instead of the usual 2,500 bunches of protons, they only used 600 bunches. Even with this reduced number, the intensity of each individual bunch was so high that it produced an average of 150 collisions every time the beams crossed. In normal operation, that number is only 65. This massive jump in collision density is a preview of the future, but it also highlights a major problem. The current detectors are being overwhelmed by the sheer volume of data, and the hardware is being stressed by the physical heat generated by these hyper-intense packets of matter. The reason most people are not aware of this struggle is because the Large Hadron Collider is often portrayed as a finished, perfect machine. In reality, it is a prototype that is constantly being pushed to the point of failure. The missing signal in the public narrative is the constant maintenance required to keep the vacuum modules from melting. The engineers are currently operating in a state of forensic intrigue, looking at every temperature sensor and every pressure gauge to find out why Beam 1 is behaving differently. They suspect that the radio frequency fingers in one specific sector have already begun to lose their spring tension, which would explain why that sector refuses to stabilize at high currents. This brings us to the importance of the upcoming long shutdown. After the year 2026, the machine will go dark for several years, for the third major long shutdown. This is when the hardware for the high luminosity upgrade will be installed. The high-intensity tests happening right now are a desperate search for unforeseen limitations before that shutdown begins. If the engineers find a fundamental flaw in how the vacuum modules handle impedance heating, they have to know now, because once the machine is upgraded to 700 megajoules, a failure would not just be a delay, it would be a catastrophic event that could damage the superconducting magnets beyond repair. To prevent a magnet quench, the safety systems have to work at a speed that is almost impossible to imagine. If a magnet loses its superconductivity, it suddenly develops electrical resistance. Because there is so much current flowing through it, that resistance creates a massive amount of heat instantly. The safety system has to detect this change in a matter of milliseconds and dump the entire beam into a massive block of graphite before the magnet melts itself. The fact that this has never happened during normal high-energy operation is a testament to the engineering, but the new heating issues are occurring in the vacuum modules, which do not have the same level of automated protection as the magnets. This is the gap in the current safety chain. What the evidence from the 40% intensity jump actually eliminates is the idea that we can simply keep adding more protons to the Large Hadron Collider without changing its physical structure. The old model suggested that the limiting factor was the strength of the magnets. We now know that is not true. The magnets are performing beautifully, even at near nominal current. The real limit is the vacuum system and its ability to dissipate the heat generated by electromagnetic wake fields. The result of the 2025 tests forces us to accept that the internal geometry of the beam pipe is the new bottleneck for fundamental physics. So, to answer the title question directly, why did one magnet refuse to settle when the Large Hadron Collider was loaded with 40% more protons? The answer is that the evidence eliminates the magnet itself as the source of the problem. The failure to settle was caused by impedance heating in the vacuum module fingers of beam 1, which created a localized heat pocket that the cooling system could not stabilize. The evidence shows that the current hardware cannot handle the electromagnetic wake of 230 billion protons per bunch without risking physical deformation. This remains unresolved because scientists still do not know if this is a single, faulty component or a design flaw that exists throughout the entire 27-kilometer ring. This verdict changes our understanding of the Large Hadron Collider from a machine limited by magnetic power to a machine limited by its own internal resistance to moving charge. It means that the path to the high luminosity future is not just about stronger magnets, but about a total redesign of how we shield the vacuum from the beam. The reverence we feel for this machine comes from its scale, but its survival depends on these tiny, microscopic metallic fingers that must remain perfectly in place while a high-speed train of energy flies past them. As we move toward the final weeks of the 2026 run, the search for these hidden flaws continues. Every time the engineers push the intensity, they are listening for the machine to tell them where it is hurting. The fact that we are even able to detect these tiny deviations in a 27-kilometer circle of superconducting metal is a miracle of modern measurement. But as the energy climbs towards 700 megajoules, the margin for error is disappearing. We are no longer just exploring the secrets of the universe. We are testing the very limits of what human engineering can contain. If you want to stay updated on how these high-intensity tests reshape our understanding of the subatomic world, make sure to follow the progress of the third long shutdown. The future of physics depends on whether we can solve the mystery of the fingers that refused to settle.